Hello, class. Today we are going to talk about electronegativity and its effect on polarity, which is the start of the. We are going to use electronegativity values to identify bonds as polar or nonpolar. And once we can identify bonds as polar or nonpolar, we're going to figure out how to identify molecules and classify them as polar or nonpolar. So first, I have a little introduction, a video demo of polarity and its effects on a balloon. All right. Credit to Vincent Sapone on that video there. It's a great one. Here we go. So as you saw, we used static electricity. There was some friction occurring there between the balloon and his arm, and then he was able to create some static electricity, which then caused an attraction with the stream of water, and it caused the water to bend towards the balloon. So we want to figure out why this is. So first we have to recap our different types of bonding. So here we have Emily and Sarah and the wonderful blanket of warmth. So Emily has a blanket, but she's too hot, so she wants to get rid of her blanket. So she gives it away to Sarah. If we're reviewing our types of bonding, we could say that that is a donation or a transfer. So that would match up with ionic compounds or an exchanging of our electrons. When we're talking polarity, we're primarily dealing with scenario B, where both of the atoms are participating in a sharing of electrons, and therefore they are covalent compounds. Now, part of the issue is this looks like they're sharing equally. But what happens when one atom is more electronegative or stronger than another? What happens when it can attract electrons better than the other atom? In that scenario, we get unequal sharing. So in scenario D, Sarah is a blanket hog, and Emily still feels decent, but doesn't get as much of that blanket. If we're looking at these two equal sharing scenarios, equal sharing is considered to be nonpolar. If we're looking at polar covalent, we have unequal sharing. Now, if we think about the word pole, like north and south pole, that means you have two opposite ends. If something is polar, it's going to have a shift, or primarily the electrons are going to be more on one side of the atom than the other. And so you create a pole where you've got opposite ends of the molecule. If you're looking at a non-polar covalent, those electrons are shared equally, and so there are no poles, north or south, in that particular molecule. So part of the ways we represent these, we use the Greek lowercase letter delta, and we use that to represent a partial. So we have a partial negative, or we've got a partial positive. So those two symbols we see here and here. When there's equal sharing, that electron cloud around the molecule is evenly dispersed. But in a polar covalent bond, we have unequal sharing. The bulk of those molecules, or the bulk of the electrons in that molecule, is going to shift to one side of your atom. So the side where more electrons occur will get a partial negative, and the sides where less electrons are will get a partial positive. Now, this is even different from our ionic scenario, because ionic is a complete transfer of electrons. Notice that these electrons are still being shared, but they're not being shared equally. So there is a slight difference there. Now, the way we can figure out how or where unequal sharing will occur is dependent on the types of atoms in our bonds. Previously, we've talked about electronegativity. That's the ability of an atom to attract electrons toward itself. We know that if an atom has a higher number of protons, it's got more positive charge within the same sublevel, and therefore it can pull those electrons in closer. So as you go across the row, you'll see that these electronegativity values do increase. Those things are in the same energy level, but the number of protons go up, so it pulls the electrons in closer to the nucleus. As we get further away from the nucleus and add energy levels, the distance causes a weaker attraction, increased distance, weaker attraction, therefore lower electronegativity. So you'll see in this bottom corner, we've got more energy levels there. Therefore, the distance is further away. You have a weaker force of attraction. It's not going to attract electrons very well. In fact, most of the things over on this side of the periodic table we know donate electrons because they're not very good at holding on to their electrons. They're not very electronegative. When we're over here, things are really electronegative. They're really good at holding onto electrons. And in fact, you could probably consider them to be greedy. So greedy for those electrons. So we have a polar bond. We know, to recap, it's in where the electrons are shared unequally between atoms. In a nonpolar bond, we have a relatively equal share of electrons between our atoms. So how do we define this? Well, polarity itself is viewed as a spectrum. The only true nonpolar bond is when an atom is bonded to itself. Because if we look at these electronegativity values, let's say I've got N2. In N2, I've got a 3.0 value for one of my atoms. I got a 3.0 value for the other one of my atoms. If I subtract them to figure out the difference in electronegativity, we get a value of 0. They're the same. So since they're the same, this is an N, sorry, a very terrible N. Since they are the same, that's the true nonpolar bond. But even if there's slightly unequal sharing, it's still considered nonpolar if our electronegativity difference is below 0.5. Now, it's not a hard and true cutoff. Honestly, something can be around the range of 0.4 or 0.5, and people will debate whether or not it's polar or nonpolar. But generally, if something is considered under a difference of 0.5, it will be nonpolar. If it's larger than 0.5, it'll be considered polar. Now, C and H bonds, for example, typically have or are typically labeled as nonpolar. If we look up the value for C, it is 2.5. If we look at the value for H, it is 2.1. If I subtract them, 2.5 minus 2.1 gives me that 0.4 value. I'm less than my 0.5, and therefore I'm considered nonpolar. Anything greater than 0.5 is considered to be polar. So now when we are doing these calculations, like say an OH bond, we're always going to take the larger value minus the smaller value. So in this one, you've got O, which is 3.5. That's the larger value minus the smaller value. And we get a difference of 1.4. This is considered to be very polar. Now, when we're trying to label where these partial negative and partial positives are, the partial negative goes with the more electronegative element. The partial positive goes with the less electronegative element. So we've got some examples here. We actually just did CH, and we classified it as nonpolar because it had that electronegativity difference of 0.4. So that's going to be your first step. Find the difference between your electronegativity values. The thing that has a higher electronegativity is going to have an arrow. And we're going to use an arrow here. This arrow is called a bond dipole. You could also refer to it as, you might see the term dipole moment. These are all synonymous. So a bond dipole or a dipole moment. The arrow always points towards the more electronegative atom, and this tail kind of looks like a plus sign, so that goes with the more positive or less electronegative element. So in this next one, we've got C and O. So if I go back to my values, I've got 2.5 for C, 3.5 for O. The difference between 3.5 and 2.5 is 1, which means we can classify this as polar. And then when I draw my arrow, I know that carbon's less electronegative. It had a value of 2.5. And oxygen is more electronegative, so it's got a value of 3.5. When I draw my arrow, I draw it just above there. The arrow points towards O because it is more polar and more electronegative. The carbon is less electronegative and gets the tail side of the arrow. If you were also labeling delta minus and delta plus, the delta plus would be here, delta minus would be there. In our next lesson, we're going to apply all of this to the polarity of molecules, and we will continue. So go through and practice those on your own, and we will check in our next lesson.